Every planet in this solar system spins the same way. Mercury, Earth, Mars, Jupiter, Saturn, Neptune, they all rotate counterclockwise. If you look down from above the North Pole, the Sun rotates counterclockwise. The whole disk of gas and dust that made these worlds was spinning counterclockwise 4.5 billion years ago. It is the most basic rule of the solar system. Everything spins the same direction, except Venus. Venus spins the wrong way, and after 300 years of staring at it, we still cannot explain why. Let me tell you what we know, because it is less than you think. Venus is almost the same size as Earth, almost the same mass. Sits right next door. If you were designing planets, you would call these two twins. Same ingredients, same neighborhood, same age. And yet if you stood on Venus and watched the sun, it would rise in the west and set in the east. Everything is backwards. That alone should make you nervous, because when nature breaks a pattern, it means something happened, something big. For centuries, nobody knew Venus was spinning backwards because nobody could see its surface. The planet is wrapped in clouds so thick you cannot see through them with any telescope ever built. Sulfuric acid clouds, carbon dioxide atmosphere, pressure at the surface 90 times what you feel standing here on Earth. Venus hides itself, and for a very long time that hiding worked. Astronomers in the 17th century tried to measure the rotation period. Giovanni Cassini, who was no fool, took a guess. Francesco Bianchini proposed about 24 days. Other people said it was probably similar to Earth, maybe a day or so. Everyone was guessing. Nobody could see a single surface feature to track. Then, in the early 1960s, we finally got clever enough to cheat. Radar. We bounced radio waves off Venus from the big dishes at Goldstone in California and the enormous bowl at Arecibo in Puerto Rico, and we measured the Doppler shift of the returning signal. Now you understand Doppler shift. If a surface is rotating toward you, the reflected signal comes back slightly blue shifted, slightly higher frequency. Rotating away, slightly red shifted. You measure the spread, and you can figure out how fast the thing is spinning and which direction it is going. Radio waves do not care about sulfuric acid clouds. They punch straight through to the rock below and bounce back with the truth written into their frequency. And when the data came back, the astronomers must have checked their instruments twice, because the signal said something absurd. The frequency spread was tiny, almost nothing, which meant Venus was barely rotating at all. And the shift was reversed from what it should have been, which meant it was rotating backwards. 243 Earth days to turn around once, slower than any other planet. So slow that a single day on Venus, one sunrise to the next, takes longer than a Venusian year. The planet finishes its trip around the sun before it finishes one rotation on its axis. Think about that. Your birthday comes around before your day is over. That is Venus. So we have two puzzles tangled together. Why is it spinning backwards? And why is it spinning so slowly? Let us take them one at a time, like good detectives. The first suspect is always the obvious one. A collision. Something hit Venus. We know collisions happen constantly in the early solar system. We have very good evidence that something roughly the size of Mars slammed into Earth about 4.5 billion years ago, and that collision is probably how we got our moon. The debris flew off, coalesced, and there it is, hanging in the sky every night. So it is perfectly reasonable to ask whether Venus got hit by something big enough to knock it spinning the other direction. And at first glance this makes sense. A sufficiently large body hitting at the right angle could reverse the planet's spin, or at least slow it almost to zero, letting other forces take it the rest of the way. The math works. You can run computer simulations where a protoplanet the size of, say, our moon crashes into Venus at a glancing angle, and the result is a slowly rotating planet spinning the wrong way. Case closed. Not so fast. There is a problem, and it is a glaring one. Where is the evidence? When something that big hits a planet, it leaves marks. On Earth, the giant impact left us the moon. Mars has a colossal difference between its northern and southern hemispheres that many scientists think came from a massive impact. Mercury has its enormous iron core, possibly stripped of its rocky mantle by a tremendous collision. But Venus has nothing. No moon, no giant impact basin, no obvious scar. The planet was completely resurfaced by volcanic activity sometime in the last 300 to 500 million years, which means the geology has been wiped clean, so we cannot rule the collision out, but we certainly cannot prove it happened either. We are left holding a murder weapon with no fingerprints on it. And there is a subtler issue. If something hit Venus hard enough to reverse its spin, it almost certainly would have generated enough debris to form a moon. Earth's collision did. So where is Venus's moon? One clever proposal, suggested by Dave Stevenson at Caltech, involves two impacts. The first collision creates a moon orbiting Venus. Then a second impact hits the other side, reversing the rotation. That reversal changes the gravitational interaction between Venus and its moon, causing the moon to spiral inward instead of outward, and eventually crash back into the planet. It is a creative idea. It is also almost impossible to test. We would need isotopic data from Venusian rocks to check, and nobody has been able to do that kind of analysis yet. So let us move to suspect number 2. This is the one I find more interesting, because it does not require any catastrophic event at all. It requires patience. Billions of years of patience. Here is the key idea. Venus has the thickest atmosphere of any rocky planet in the solar system, 90 times denser than ours. And Venus sits close to the Sun, closer than we do. The Sun's gravity is pulling on Venus, trying to slow it down, trying to lock one face toward the Sun permanently, the way our moon always shows us the same face. This is called tidal locking, and it is what gravity does given enough time. It slows you down until your day equals your year, and then you just sit there, one side always lit, one side always dark. But Venus is not tidally locked. Its day is not equal to its year. It is close, but not quite. Something is fighting back, and that something is the atmosphere itself. When the Sun heats Venus's thick atmosphere, it does not heat it evenly. The side facing the Sun gets hot. The side facing away stays cooler. This creates a pressure difference, a redistribution of atmospheric mass. The heavy atmosphere bulges toward the cooler side, away from the Sun. And because Venus is rotating, that bulge is not perfectly aligned. It is shifted slightly, and that misalignment creates a torque. The atmosphere is pushing the planet, not forward, backwards. The thermal tides in Venus's atmosphere generate a force that opposes the Sun's gravitational tidal locking. It is like two people arm wrestling. Gravity says slow down and lock. The atmosphere says no, keep going, and actually go the other way. In 2001, two French astronomers named Alexandre Correia and Jacques Laskar published a remarkable paper in Nature. They ran simulations of Venus's spin over billions of years, taking into account the gravitational tides from the Sun, the thermal atmospheric tides, friction between Venus's core and its mantle, and the gravitational tides of other planets. They tried thousands of different starting conditions: fast initial spins, slow initial spins, small tilts, large tilts, and what they found was surprising. Regardless of where Venus started, regardless of how fast it was spinning initially or which way it was tilted, the planet could only end up in one of 4 stable rotation states. 4. Out of all the infinite possibilities, the physics funnels everything down to just 4 endpoints. And most starting conditions led to the state Venus is in right now, slow retrograde rotation. That is an extraordinary result. It means Venus might not have been knocked backwards at all. It might have been born spinning perfectly normally, like all the other planets, fast and prograde, and then over billions of years. The tug of war between solar gravity and atmospheric thermal tides gradually slowed it down, slowed it further, brought it nearly to a halt, and then gently reversed it. No collision required, just physics and patience. But Correia and Laskar also showed something else. There were 2 different paths to the same destination. In one path, Venus's rotation axis tilts all the way over to 180 degrees, flipping upside down, so the planet is technically still spinning the same direction, but is now inverted. In the other path, the spin itself slows to 0 and reverses, while the axis stays put. Both paths lead to what we observe today, and we cannot tell which one actually happened because both produce exactly the same final state. You see the difficulty? We have 2 completely different histories that produce one outcome. The planet does not remember how it got here. It only knows where it is. Now let me complicate things further, because nature always has more layers than you expect. Venus's atmosphere is doing something else that we cannot fully explain. The planet takes 243 days to rotate once, but the atmosphere at the cloud tops goes around the entire planet in just 4 days. 4 days. The atmosphere is moving 60 times faster than the surface beneath it. This is called superrotation, and it is one of the most puzzling phenomena in planetary science. On Earth, friction keeps the atmosphere more or less in sync with the surface. The air moves, of course, we have winds and storms, but the overall rotation of our atmosphere roughly matches the rotation of the ground. On Venus, the atmosphere has essentially decoupled from the planet. It is screaming around at something like 224 miles per hour at the cloud tops, about 65 kilometers up, while the surface below barely creeps along at walking speed. Down near the ground, the winds are gentle, just a few miles per hour. But as you go up through that immense column of carbon dioxide, the speed builds and builds until the cloud layers are lapping the planet 60 times faster than the planet turns beneath them. Nothing else in the solar system does this so dramatically. Titan, Saturn's big moon, shows a mild version. But Venus is the champion. And we are still working out exactly what drives this. Thermal tides from solar heating play a role. The sun warms the dayside atmosphere. The hot air expands and loses pressure, and the pressure difference drives winds screaming toward the night side. Planetary scale waves, the kind of organized disturbances that ripple through any rotating fluid, transfer angular momentum around. Recent data from the Japanese Akatsuki spacecraft, which has been orbiting Venus since 2015, has helped map these winds in detail for the first time. The picture is clearer now than it was a decade ago. But a complete explanation, the full accounting of where the momentum comes from and how it sustains itself against the friction of the surface, is still missing pieces. What we do know is that the super-rotating atmosphere acts like a brake on the planet's rotation. A recent study by Stephen Kane argued that without the atmosphere, Venus would have continued slowing until it tidally locked to the Sun. The atmosphere prevents this. The Sun's gravity wants to lock Venus in place, but the Sun's own energy heats the atmosphere, making it dynamic, making it push back. The very force trying to stop Venus is also powering the mechanism that prevents the stop. There is something almost mischievous about that, do you not think? The Sun works against itself. And here is where I want you to pay close attention, because this is the part that matters most. We do not know the answer. I could stand here and tell you it was a collision, and that would be a respectable position. I could tell you it was tidal evolution driven by the thick atmosphere, and that would be equally respectable. I could tell you it was some combination of both, an initial collision that slowed Venus's spin, followed by billions of years of atmospheric and tidal forces refining the rotation into its current state. That hybrid model has supporters too, but the honest truth is that we lack the data to distinguish between these hypotheses. Venus's surface was completely repaved by volcanic activity a few 100 million years ago. Whatever scars a giant impact might have left are buried under kilometers of lava. We have no rock samples from Venus to analyze. We have no seismic data from its interior. We do not know whether Venus has a solid or liquid core, or whether it has plate tectonics of any kind. The Magellan spacecraft mapped the surface beautifully, with radar in the early 1990s, and the Venus Express mission studied the atmosphere for years, but there are enormous gaps in what we know about this planet's history and internal structure. This is important, and I want to say it plainly, because I think there is a lesson here that goes beyond Venus. In science, the willingness to say we do not know is not a failure. It is the beginning of honest work. Too many people rush to fill silences with confident explanations that sound satisfying but rest on sand. Venus spins backwards. We have good ideas about why. We have mathematical models that are consistent with observations, but we do not have proof, and claiming we do would be lying. What we do have is this: a planet almost identical to our own, sitting right next door, doing something that no simple theory fully explains. A planet whose atmosphere moves 60 times faster than its surface. A planet where the sun rises in the west. A planet with no moon, no magnetic field to speak of, surface temperatures hot enough to melt lead, and a rotational history that might have been shaped by a catastrophic blow or might have been shaped by nothing more than sunlight pushing air. Both stories are beautiful. Neither is confirmed. Future missions may change that. NASA has approved Veritas and Da Vinci, two spacecraft designed to study Venus in unprecedented detail. Veritas will map the surface with high-resolution radar, looking for clues about the planet's geological and possibly impact history. Da Vinci will drop a probe through the atmosphere, sampling the chemistry on the way down. If we can get isotopic ratios from Venusian rocks or atmospheric gases, we might finally be able to tell whether a giant impact occurred. If the ratios look like the aftermath of a massive collision, the impact hypothesis gets a huge boost. If they look like a planet that formed normally and drifted into its present state, the atmospheric tidal model wins. Until then, Venus keeps its secret, and I find that thrilling, not frustrating. Thrilling, because the universe does not owe us easy answers. A planet that hides behind acid clouds and spins the wrong way and defies 3 centuries of telescopes is exactly the kind of problem that makes you glad you got into this business in the first place. So here is what I want you to sit with. Every planet formed from the same spinning disk of gas and dust. They all inherited the same angular momentum. They should all rotate the same way, and yet one of them does not. Why? We have suspects. We have theories. We have computer simulations. We do not have a verdict. And the next time someone tells you with absolute confidence why Venus rotates backwards, ask them one simple question. How do you know? Because right now, nobody does. And that open question hanging in the dark is the most interesting thing in the solar system. Tell me, which explanation do you find more compelling? The violence of a collision, or the slow patience of an atmosphere pulling a planet backward over billions of years? I would like to know what you think.